So, this course has been largely about planar mechanisms, where all the points on the mechanism move on parallel planes. And a majority of real life mechanisms fall into that category. So, you can actually, lot of the mechanisms that you will encounter can be planar mechanisms. However, there are some special applications where you may need a mechanism which has, where the point paths are not in parallel planes, but you need them, you know, it is general 3D space. Okay. So, they have general 3D point paths, and these kinds of mechanisms are called spatial mechanisms, where the motion, so you have, you can't view the motion from just one direction. Okay. So, in any planar mechanism, if you view the mechanism from the direction that is perpendicular to the plane in which the motion is happening, you get the complete picture of the motion. That is why most real life mechanisms, even though they are solid, you know, they are, you can view it from a single plane, like your folding chair. Okay. You can view the mechanism just from the side, you do not need the whole. So, we say those 3D or spatial mechanisms are built by stacking planar mechanisms. That is not what we call a, so we would still deal with that as a planar mechanism, we would not call that a spatial mechanism. A true spatial mechanism has point paths which are in 3 dimensions. So, take for instance, this is like an agitator mechanism in a washing machine. Okay. You can see that there is no single plane from which you can view this, view the motion of this mechanism or describe the motion of this mechanism. Okay. This YouTube channel of this person Thang has some very nice animations. He has created animations of several mechanisms. You should go see some of those. It's a very nice. So, I asked him for permission to use some of these videos, and he agreed. So here is your wheel retraction in an aircraft, you know, but it is not just happening in a plane. So, you can see that this is, you have a revolute joint and you have this link with 2, and then you have a slider. The wheel retraction mechanism. Okay. And there's a, here's another example. This is a mechanism for, can you guess, making dough, chapati dough. So, they can, so in big bakeries or, you know, things like that, they will have mechanisms that will do this. Let me just put it on repeat. So, it lifts it and, you know, does the kneading of the dough. Okay. So, so there are applications where you know, spatial mechanisms are used. The spatial version of the 4-bar. Okay, wait a minute. Let me show you this. This is our good old 4-bar, but in a spatial form. Okay, the spatial version of the 4-bar. So, you have the links are all in different colors. You can see the bearings, these are the, that is the fixed link. So, this is a spatial 4-bar. So, you have other examples. Can you think of any examples you may have seen of spatial mechanisms where the motion does not just happen in one plane? Other examples? Can you? That you may have seen? Not necessarily linkages, but anything where you can't describe the motion in just one plane. Bevel gears, yes, yes. So, the worm gears, bevel gears, they are all see bevel gear, it is like two perpendicular axes, right? Yeah. So, you could, yeah, you can't observe the motion from so bevel and worm gears.
Hook's joint.
Hook's joint, yes, I have a video of that. Okay, Hook's joint, where you have two joints that are at different angles and you are transmitting rotary motion from one to the other. That is a good example of a spatial mechanism.
Opposite joint. Opposite joint. It is again for perpendicular power transmission.
Right, right, right. How do you spell that? Hobson joint, okay. CV joints, yes. So, a lot of these transmission joints, you know, where you have shafts which may intersect, the axis may intersect, may not intersect, you know, all kinds of combinations. When you want to transmit rotary motion from one shaft to another, a lot of these joints are actually spatial mechanisms, because and you may also need it to, even if they are expected to be, you know, somewhat aligned, you may use something like this, so that you can take care of any misalignments in the shaft. Okay. You do not want things to bind up. So, any constant velocity joint, Hook's joint is not constant velocity, but there are other what you know in general term we call as the universal joint, U joints. Universal joints, they all fall under these. What else can you think of?
3D gears.
Yeah. So, 3D we have already mentioned some gears. How about something close to you? Can you think of anything that you use every day? Bicycle. Bicycle is planar, more or less. Bicycle, most of it can be described using planar. I'm talking really close to you. Human, the arm, right? So, as I am writing, my arm is making a closed loop mechanism, right, and I can't describe the motion in a single plane. So, as I am writing, I am actually closing the loop. All robotic manipulators are also 3D, many robotic manipulators are 3D mechanisms, but in many of them they may be open loop mechanisms, but even if you look at like a closed loop, when I am doing something with my arm, okay, it forms a closed loop, right. So, that is human arm is another good example of a spatial mechanism. Okay. So, and then you may have heard of like Stewart platforms, right, they are parallel manipulators, parallel manipulators. Okay. So, these are all examples of spatial mechanisms. Okay. Cylindrical cam, that is all again, you know, you would have seen with a groove on it, and then it has, you have a cylinder with a groove on it, and that is moving the follower moves in the groove. So, that is an example of a spatial mechanism. Okay. So, just as you have in planar mechanisms, you can have revolute joints in spatial mechanisms. revolute joint. So, it is typically designated as R in a spatial mechanism, and its symbol would be, so in a spatial mechanism you would represent it like this. We have one link. So, this shows that it can only rotate with respect to the other link and not translate. Okay. So, so if this is your 3D representation, 2D representation we just showed planar, this is how we show the revolute joint. How many degrees of freedom do you have? Only one. The revolute joint still has only 1 degree of freedom. This is my prismatic joint, right. So, this is prismatic and here no rotation is allowed. Yes.
Given two links, I can choose any axis of rotation. In this case, the axis of rotation coincides with one of the link directions. So, in general, how do I represent a 3D revolute joint? I can also have the in-plane rotation even in 3D, right?
No. So, you have one link, you have another link.
Yes.
When you connect them by a revolute joint is such that it allows only rotation of one link with respect to the other. That is the only motion that is allowed. When you connect them by, it does not matter what the direction of the axis is.
Yes.
So, when I have a revolute joint, it basically restricts all other degrees of freedom between the two links. It only allows this motion. I can have something pointing in some other, that will be the axis of rotation of the joint, but the only motion that is allowed is rotation about that axis.
So, if I want to represent the two-dimensional hinge in 3D, I use the same symbol.
Yeah.
Okay.
Yeah. So, this is the general representation of a revolute joint. So, for a prismatic joint I have to arrest the rotation. So, if this is one link, okay, one can move only, it can't rotate with respect to the other. So, this is the general prismatic joint. In 2D we showed it like this, right. So, that is the 3D representation. Again this is also a 1 degree of freedom joint. There is no rotation is not allowed between the two links. Okay. In the case of the cylindrical joint, you have 2 independent degrees of freedom. So, this would be the representation. This link, you can see here that I do not have these bars that denote the revolute joint. So, it can have sliding and rotation. So, it is a 2 degree of freedom joint. This is a cylindrical. Okay. So, this is a 2 degree of freedom joint. And what would be the planar representation of this? It is not a planar joint. You do not encounter it in planar mechanisms because you have motions in 2 different directions. Okay. Sliding takes place in one, the rotation is observed in another plane. So, because of that this will not, you will not encounter this in planar mechanisms.
We consider pin joints as higher pairs if it is planar.
Let me repeat. Question again, do you consider pin joints as?
When we have pin joints in planar,
Yes.
but it's also similar to cylindrical.
No, if you have a pin joint, like this, if I connect two links with, so yes, you would have a pin that goes through like this connecting these two links like your door hinge, right. You do not allow this motion. If it is a revolute joint, I will not allow this motion. It cannot slide, one link cannot slide with respect to the other.
But it moves along a slot.
What moves along a slot? So, if it is a revolute joint, the only motion that is allowed is this. I cannot allow this motion. If I allow this and this, then it is a cylindrical joint.
It is asking for slot in a pin. Sorry.
You are asking about a pin in a slot. Okay. So, when you look at a pin in a slot, so you have a cylinder. Thank you for. So, your question is that a cylindric joint?
It's also cylindrical.
It is not a cylindric joint, because, so if I have a slot and I have a pin, this rotates, I can see the rotation in this plane, the translation is this way.
Yes.
You are observing both the motions, there is no translation perpendicular to the plane.
Just because it's not in 3D, can it not be cylindrical at all?
This is not a cylindric joint. A cylinder's definition is where you have to, this is a planar cam joint. We call this a planar cam joint.
So cylindrical is defined as it should be in 3D and it should have a revolute and
It, the axis, yeah, the axis of rotation and the axis of translation coincide. Okay, so it is translating along the same axis about which it is rotating. So, the cylindric joint, the axis of and axis of translation coincide, right. The cylinder has only one that axis. So, there is translation happening about that axis as well as rotation about that axis. On the other hand, this is the planar cam joint, pin and slot, right. Here the axis of rotation is perpendicular to the plane of observation and the axis of sliding is also different. Okay, the two are different, but thank you for clarifying the question. Okay. And what is the number of degrees of freedom of this joint? Is 1. We have seen, because the helical joint has DOF 1, because the translation and the rotation are related by the pitch of the screw. So, actually the lead of the screw. Okay. So, you have a definite relationship between the two and therefore, it is a 1 degree of freedom joint, but again the axis of rotation and the axis of translation are the same here, like the cylindric joint, but in the cylindric joint the two are independent, I mean the two motions are independent. Here the two motions are related, degree of freedom is 1 and you have, so your representation would be and it is not a planar joint. Not a planar joint. So, there is no planar representation for us. This is your spherical, sometimes called, referred to as a globular joint. So, the Dennewitt book refers to it as a globular joint. This is your ball and socket, ball and a socket joint. How many degrees of freedom? You have 3 degrees of freedom, and the general representation. So, you have a ball and you have a socket. Common examples you know, in the human body, your shoulder, your hip, these are common examples of a spherical joint, or nearly spherical, because in the human body you do not have a perfect sphere going into a perfect
In application,
capsule. Yes, and I will show you lots of applications for spherical joints. Okay, and this is the planar joint. Okay, so in your mini drafter, the scale that's connected, okay, as it's moving, you have the rotation as well as the translation of that. Okay, so that is an example, or a duster on a board, right? So that would be an. So if I was cleaning the board with the duster, okay, my arm would form a mechanism where the joint between the board and my hand is a planar joint, okay, because I can move, assuming I take the duster as attached to my hand, then the joint between those two links is a planar joint when I am cleaning the board. Or even here as I am writing, that's a planar joint. I can move x, y and rotate. Okay. So, this is a 3 degree of freedom joint, and its general representation is just a plane with another thing on it. Okay. So, typically planar mechanisms are represented in terms of the joint. So, this would be like an RSSR mechanism. So, this is essentially a 4 bar. Okay. You have this link. So, this is link 1 which is fixed, then you have link 2 which is the crank, and then you have a link 3. You can see so the joint between link 2 and 1 is an R, is a revolute pair. The joint between links 2 and 3 is a spherical joint. This is your, here they call it globular, but that is a spherical joint you have, and then again the joint between 3 and this is link 4, that is also a spherical joint, and then 4 and 1 it is a revolute joint. So, this would be typically referred to as an RSSR mechanism. It is a 4 bar. It is a spatial 4 bar could be an RSSR mechanism. I think I have a video of that. Let me show you that. You can see there. So, you can see this is the link that has spherical joints on either side, then you have, so this is your RSSR 4 bar, spatial 4 bar. Okay. Now, we can do a similar mobility analysis for spatial mechanisms, except that you have to take into consideration the fact that now a rigid body in space has how many degrees of freedom? 6. Okay. When we restricted it to the plane, it only had 3 degrees of freedom. Now, you are talking about a general rigid body. So, if you take n links and make a mechanism, you would fix one link. So, this would be the total number of degrees of freedom, and then I start adding joints, I start adding constraints. So, if I add a joint with a single degree of freedom, that is my like a revolute joint or a prismatic joint. What is it doing? How many constraints is it imposing? It is removing 5 degrees of freedom, right? It is allowing only one, that means it is imposing 5 constraints. So, for every J1 in the mechanism, I am losing 5 degrees of freedom. So, that is what this means. Similarly, if I have J2, if it allows 2, it is taking away 4, and so 4 J2 would be the number of, and so on, J3 to J4, J5. You could have something, you could have like a ball and socket that can slide in 2 different directions in a slot which allows sliding in 2 different directions. So, that would be a joint that allows 5 degrees of freedom, okay, like your pin in a slot, right. So, if you had a ball which was in a slot that would allow sliding along 2 different directions, then you would have a J5. Okay.
In any situation, if there are 2 different directions which are going to allow the ball.
So, it is like a planar, it is a planar. So, it will allow in two.
In one direction I can understand, as soon as I increase it to 2 directions of translation, the ball can come out.
What if that itself can slide? So, it is the ball is in a slot.
Understood.
Okay. So, the ball can slide within that slot, but that slot can slide in another direction in the plane. So, that becomes a composite joint which has 5 degrees of freedom. Okay. So, the yes.
Here the coupler's rotation about its own axis.
So, we are coming to that, we are coming to that. So, now if I look at this 4 bar, okay, let us do the mobility for this RSSR mechanism. Okay. So, my N is 4, how many J1s do I have? 2, the 2 revolute joints. How many? I do not have any J2, J3, 2, I have 2 ball and socket spherical joints, right. So, now if I do the mobility, if I apply the mobility equation, what do I get for the mobility of this mechanism? I get a mobility of 2, but it is quite clear that it only has, you know, that there is a definite relationship between the input and the output. You need only one input to make this mechanism move in a predictable fashion. The input angle, output angle can be related directly, which means there is an additional degree of freedom. What do we call that which is not affecting the input output relationship? We call it an idle degree of freedom. So, what is this idle degree of freedom here?
Rotation of the coupler.
Idle degree of freedom is the rotation of coupler about its own axis. So, I can keep this mechanism in this position and I can just spin that coupler, right. I can spin this coupler and it will not affect the input output relationship. So, that makes it an idle degree of freedom if with this input and output. Okay. So, because it the equation is not wrong, this mechanism does have 2 degrees of freedom. Functionally, we are only concerned about this as input, this as output. So, functionally it has it is a mechanism of mobility 1 and it has an ideal degree of freedom, which is the motion of the coupler about its own axis. Okay. So, if you had to draw the kinematic diagram of, you would draw it something like this. So, this could be moving in a circle like this and this. So, you would have, so your R, S, S, R.
So even for these 4 bar, are there 2 linkages, a cross version and a straight version?
Depends on what you define as cross and straight here, right? Everything is,
So this also has multiple branches. Can have multiple branches.
it could have multiple branches, yeah. Okay, the displacement analysis, the analysis of spatial 4 bars is a lot more complicated then. But yeah, if you just take, so for instance, you just take a planar 4 bar, okay, and I put, instead of making a revolute joint, I can always put a spherical joint there, right. So, I can have 2 branches of this. Okay. Why would I do something like this? Sometimes, and in fact, they do this even for some planar applications to handle misalignment. So, they will put, because of manufacturing errors, there could be misalignment. So, for instance, your steering mechanism will have this kind of an arrangement. Okay. So, they may use, even in planar mechanisms, they introduce these additional ideal degrees of freedom because it can help to handle misalignment. But there is a very specific relationship between input and output. Do you have a question?
He applied this equation for a planar case.
Ah, okay. I'll let you think about that. We'll talk, yeah. Why doesn't this, if I apply this for a planar case, it won't work?
Because I forgot to count 4 planar joints.
Because you are applying the same constraint to multiple planar joints. So, they are not really independently taking off any, so you will actually get something that is over constrained.
5 constraints on each and every independent link are dependent.
Yeah. So, so the question here is, why doesn't this equation apply for a planar mechanism? If I take a planar mechanism, planar 4 bar and apply this, what will I get? I get minus 2. I will get an over constrained mechanism. So, that means there are 3 extra constraints. See, one is, I know the mobility of that mechanism is 1, but I am actually getting minus 2, which is 3 less. That is because when I restrict it to the plane, okay, I have already said that is my axis. So, the other 3 joints, the other 3 single degree are not really, when you apply this equation, they are also taking away 1, whereas they are not independent, right. All of them, it is the same constraint applied to all 4 joints when you restrict it to the plane. So, you do not apply this criterion, the spatial mobility criterion, to a planar mechanism. Good question. Okay. So, this is your some more examples. So, a special case of the spatial mechanisms is when all the axes of rotation intersect at a point. And so, you see here this is your hook joint, this is your hook joint. You can see that it is transmitting from one shaft to another, and you have this is a 4R mechanism. Okay. This is another version of it, and we call these spherical mechanisms because all the points move on concentric spheres. Okay. You can see that the axes always intersect and the motion is spherical. So, these spherical mechanisms are a special case of spatial mechanisms.
This is also the same one, right?
Yeah, yeah. So, but this shows that spherical nature nicely. Okay. And then you can have other mechanisms. So, this is like a twisted 4 bar, it is a special mechanisms called the Bennett Mechanism. So, I just wanted to show you that. I do not know of any applications of this, but this is the spatial version of a slider crank. This is your spatial slider crank. I want you to identify the joints and calculate the mobility of this mechanism. So, tell me how you would designate this mechanism in terms of the joints. This would be a R, okay, RS, okay. Somebody says RS, RC, RS, look at what is happening there. Look at this, what is happening there. If you look at this side, then you can see what is happening with that. Look at this end. So, he is right, it is an RS RC. You can see this thing keeps this rotates also, rotates and slides. So, this is a cylindric joint between these two. So, now do the mobility for this. This is a J1, this is a J3, this is a J1, this is a J2. What do you get for the mobility? Are you sure? The mobility of this mechanism is 1. So, this is a spatial slider crank. Mobility 1.
So is it not more efficient than the original slider crank? Inefficient.
If we want it, so his question is it more efficient than the planar slider crank?
Less efficient, ma'am.
Less efficient, okay, less efficient, you will have to then define efficiency, okay. So, let us not go into that, we can have the discussion later, okay, because we need to define what is efficiency first, if we are going to talk about efficiency, okay. So, here this is another slider crank. RSSP. And what would be the mobility of this one? The mobility of this one, it is similar to the RSSR, right. So, this is an RSSP slider crank, okay, and its mobility is 2. Why is the mobility 2? Because it again there is predictable input output motion, but again it is the connecting rod, the coupler can spin about its axis. So, you have one idle degree of freedom, coupler spinning about its axis, which does not affect the input output relationship. Okay. So, you will find in many cases where you have two spherical joints in series, it is likely that you will have an idle degree of freedom, okay, unless for some reason that is desired or that is required, okay, that is part of the output that you are looking at, okay, then it is an idle degree of freedom. If this is attached to some kind of an indicator or something, if that motion is of consequence, then you would not call it an idle degree of freedom essentially, okay. It might need some, then you would need an additional input to the mechanism essentially, because when you have mobility 2 you need 2 inputs. Here you can get away with one input because the other one, it does not matter what the orientation of that coupler rod is, okay. Otherwise you would say that that is an additional input you have to give the mechanism, okay. So, that we will start looking at the matrix method for analyzing. I am just going to go over some basics of transformation matrices and how they would apply to mechanisms. Robotics courses are much better equipped to give you the full, we obviously do not have the time to go over the entire analysis of spatial mechanisms, but there are I think several robotics courses that you could, they are dealt with better in robotics courses using, but I'll talk to you about the basics of transformations. So, when you have, just to give you a brief preview, I mean it's when you have links that are oriented in space, then it is easier to what you typically do is you attach a coordinate frame rigidly to each link, okay, and then you establish a relationship between those coordinate frames, okay. You have these things moving with respect to each other. The reason it is convenient is that if there is a frame that is rigidly attached to a link, then all the points on that frame can be easily described with respect to that coordinate frame, and it is not going to change as the linkage moves. So, I know the relationship. So, if I have a coordinate frame attached to my forearm, I know exactly where my wrist is with respect to that, or wrist or elbow or any other point on my forearm. If I know the relationship of this coordinate frame to say the ground coordinate frame, okay, then at any instant if I want the position of my wrist, as long as I know the relationship between the two coordinate frames, I can find my position of the wrist globally, okay. So, that is the idea behind in robotics you attach coordinate frames and then establish the relationship between those coordinate frames, because then it becomes easier to describe the motion of all the points that are of interest, because the points that are of interest on a specific link will be completely known with respect to the coordinate frame on that link. That is how you relate the various. So, if you have a manipulator, you have the gripper, right. If you know the relationship of the gripper coordinate frame to the ground coordinate frame, then specific points on the gripper become easy to describe. Okay, points, then positions, velocities, acceleration, there is a whole, we will not go into those details in this course, because we are nearing the end of this course, and our purpose really was to look at planar mechanisms. So, this is basically just an introduction to spatial mechanisms, and so we will I will just introduce you to that concept in the next class. Yes.
In this slider crank,
Yeah.
if the prismatic axis and the revolute axis are aligned, the slider won't move. Right?
One second. In this slider crank, yes.
The axis of the revolute joint and the prismatic joint aligned,
Yeah, they are aligned here, right?
as in coincide.
When this, yeah, if you are saying if this axis, yeah,
When
Yeah.
they coincide, the slider won't move. Right?
yeah,
Why is that? The
because
mobility
it is a singular point, no?
But the mobility will
See,
still-
because it's everything is in line, it's like a toggle position, right? Everything is in line, so what are you going to move? You're saying you're saying everything here is moved. So, here you do not have this offset, you do not have this link at an angle. So, you are saying I have a revolute joint, I have this revolute axis, then I have this, and I have the slider moving like
Ma'am,
this.
the spherical joint can be below. It's just that the revolute axis and the prismatic axis are aligned.
So
Spherical,
the first globe moves on the rim
Moves
of a
up
cone
and
and the
aligns
second
with
one
the-
stays at the vertex of the cone.
so you are saying it's something like this?
No, ma'am. He said that the second globe stays at the axis and the first globe stays at the offset. So the first one moves in the cone and the second one stays at the vertex of the cone.
Yes, ma'am.
Like that,
Yes.
So
okay.
it does not create anything.
So even if we rotate the input, the slider will still remain stationary.
It will move in the cone and the vertex does not move. Because the slant length is always
It will move on the,
cone.
so it's like a degenerate case, right? That you are, I mean, it still moves, moves in the sense it remains stationary. That is the relationship between your input and output. When you are moving this in a cone, and that is along that, the vertex of the cone remains where it is. What would be the purpose of this mechanism?
If you want to disengage a clutch or something, you can just shift it to the cone and then the rotation will not move further. It will stop there because of the singularity. But I don't think they use this for
I don't know if they use something like
This
this.
would be too complicated.
But the mobility still comes out as 2.
The mobility still comes out as 2, yeah, because there is nothing, see, the geometry is what is preventing the movement. That is, so the output is, for whatever angle of the input, it is 0. That is the specific relationship between the input and output. There is a specific relationship between input and output, which means it has, it is not a structure. It is not mobility equal to 0, where it can't move, because you are moving this link. Okay, there is a specific relationship between the input and output. That is what you have here. And this rotation also exists. I can spin this, and again that does not change anything. So, the mobility still remains the same. Okay, so it is a special case of of 0 output movement, like your dwell, right. See, we do not say just because a mechanism encounters a dwell, you do not say it is no longer a mechanism there. This would be like a dwell position. So, like he said, if there is some way you can change it and you do not want it to move, then this would be some way of doing that.
I can synchronize the vertical
So, it would be a way to create a dwell in the mechanism, for instance.
If we define as we need two like inputs to position all the linkages, we at any position we need two, the angle and the position.
Yes, yes,
So
yes.
if we go with that definition,
Yeah. So, because you know you may be, this may be in some way, this may be operating something else. As this slider crank is moving, you may want to use this degree of freedom to operate something else, in which case the orientation of that probably matters. It is no longer an idle degree of freedom, because you may have to actually specify. So, this could be connected to something else, right? It could be connected to another linkage, and the rotation of this may actually be the output of something else. It is possible, in which case you are going to have to control that rotation. So, anytime you have a degree of freedom, it is an opportunity to control the mechanism. When you say it is an idle degree of freedom, what it means is, okay, for this input and this output, I do not care how that thing is moving. But if that matters, then you have to control that. You have to give an input there which will influence some other output. As far as this relationship is concerned, it is idle, may have some other use.
Spatial cam. So like the
One.
previous 4 bar, the crank rocker,
Yeah.
we can't actually take a projection of the mechanism to make it a planar, right?
Which one?
In this thing slider crank, we can't just project it like the previous one.
Yeah.
Yeah. So if we change the like axis of rotation of the crank one,
This one you are talking about, this one or the next one?
no, the previous one, the crank rocker, the normal crank rocker.
The 4 bar.
Yeah, the 4 bar, the normal one.
Yeah.
Yeah, here we can just take a projection of it and like visualize it as a normal 4 bar, right?
So, it depends, right? It depends on how the revolute.
revolute
So,
is, yeah.
that is what here that is a case.
Yes.
I could have these two revolute axes parallel to each other, okay, in which case I can visualize it as a planar with just additional.
So as we mentioned, those are the cases where offset is 0 and the case which you consider is offset non-zero, right? So if I change the axis of rotation of the crank to
Now which one are you talking
the
about?
last one, the last one, the last
Okay, this is a 4 bar,
one. This is just a projection,
this is the projection.
but that is not. The one which we were discussing is not.
Okay, let us go to that.
Here we don't have a projection like that because the axis of revolute joint is different. So if I rotate the revolute joint and make it like basically in the same plane.
You want to make this into a planar mechanism. You already know how to make a planar slider crank. What are you trying to do?
Basically there are spherical joints, still there are spherical joints.
Okay.
But I just want to rotate
And
that.
if I can do that, no, I can replace any revolute with a spherical. See, I can have this, I can put a ball
Yes. So this won't face the same issue, right? The
like
offset
this.
0 problem.
Now how would I create a planar? Okay, so attached to this slider, a ball attached to this slider which moves.
So this won't have the same issue, whatever we were facing here, right? The offset 0 problem.
But the axis.
No, he is still talking about a planar thing. See here when this moves, okay, when I rotate this crank, this is going to move on a cone.
Yes.
Okay, so the distance, this block will not move. So his question was, okay, if it does not move, does the mobility equation still apply for this case? Why is it not showing mobility equal to 0? Again, special geometry, right? It is not a structure where nothing moves. If you have mobility equal to 0, nothing moves in that. Like you have a truss, 3 links pinned together, nothing moves. Here you are moving the input link, you have no motion of the output link. It is a special case of movement where you are getting a dwell. Mobility is still 1. for this. In this case mobility is still 2 because you have that other independent motion about the coupler axis.
The slider doesn't move there, right? So if you fix that slider, so it still is a mechanism, it still moves.
Yeah.
So
Yeah.
that will become a 3-link mechanism, right? So in spatial, 3-link mechanisms are possible.
Yeah. So that's exactly what you did here, no? In the special case, special geometry, always, you know, you can always play around with the geometry to come up with something special. Like you have your 4 bar, right? Typically your coupler has complex motion. You have a parallelogram linkage, your coupler has only translation. You can always play with geometry. That's always possible. So yeah.
The question is, in 2D we don't have three-link mechanism. Here we have.
Minimum of links should be 4 in.
Yeah, but this is a very special, I mean what are you accomplishing with this mechanism, right? I mean it is a 3-link mechanism, true, but you know, and that is because yeah, of the special geometry.
How is it a 3-link? It's still 4, right? Violet, white.
See, you could still have a 3-link mechanism in 2D when you have a pin in a slot. If you look at a pin in a slot, so if you have a higher pair for instance, you can have cam and follower, that is a 3-link mechanism, it is a planar mechanism. So it is not that you do not have, see when we talk about the mobility Grubler's criterion or whatever, we say specifically that it is simple hinge joints. We very clearly define what are the conditions in which the Grubler's criterion. Then you need minimum 4 links. If I want higher pairs, a cam follower is a cam follower and the fixed link, it is a 3-link mechanism. Fixed link, the fixed pivots for the cam and the follower to rotate about.